We're very happy to have Soumya Sankar, who's going to be talking about curves over finite fields. So you can take it away. Thank you.
Awesome. Thank you so much, Alvaro, and thank you for giving me the opportunity to run this course. I'm like really glad to be here. I was at CTNT 2016 as a student, and it was one of the most important summer schools I attended as a grad student. So it was a great experience. And it's really sad that we can't all be in stores in person. But what are you gonna do, right? Okay. And of course, I should like um, the organizers deserve a lot of credit for because like organizing a conference is a huge amount of work, and transferring all of it online is a massive undertaking. And they did a fantastic job. Um, so I'm gonna lead the course in curves of finite fields. My lecture notes are already on Piazza, so you should be able to find them on the resources tab on Piazza. Um, and there's a bunch of exercises that are within the body of the notes that sort of fit into the narrative, but there's also some extra ones that are a little outside or are more like supplementary material, which are at the end of the lecture notes. Now, these are still a work in progress, so I'm going to keep adding more exercises, and don't feel pressure to do all of them while during CTNT. The great advantage of everything being online is that you can look at things later. So if at some point, attending an online workshop is hard, or an online summer school is hard, it's more exhausting than you think it is. So if at any point you need to like step back and like step away from screens, um, absolutely you should feel free to do that. And yeah, so remember to take care of yourself. It's very easy to like get excited about all of the math and then forget to like eat properly and drink enough water and sleep well. So make sure you do all of those things. Um, okay, great. Um, so let's get started. So the plan for today is to talk about elliptic curves over finite fields. Um, and uh, the main reference, so I'm going to talk about various aspects of elliptic curves. Of course, one could write a book on this, and there are multiple books on this. Um, and so the main reference for this is going to be Silverman's book. I've tried to put um, most of the stuff that you need in the lecture notes, or at least like a link to them or something. But if you don't have access to Silverman's book, then let me know and we'll find a way of working around it, right? So this is called Arithmetic of Elliptic Curves. This is the canonical text on elliptic curves. Um, so that's the main reference. Okay, great. So just to start, let's set down some notation, right? So FQ is going to be a finite field with Q elements. Q elements. Um, Q is going to be a power of P, where P is a prime, right? Um, right. So one of the most important maps that we will come across in characteristic P things is the Frobenius map, right? So it's a map from FQ to FQ that sends A to the Q, right? And this map,
Soumya,
yes.
there is a question. Let me see if somebody wants to ask one question. Hold on.
Hello, I have a question about Silverman's elliptic curves book. So I was looking at it, and I was thinking about reading it this summer, but I noticed it uses a lot of references from Hartshorne that go through up to about 300 pages of Hartshorne. Do you think you need to read Hartshorne before you read Silverman?
I did not. I still have not read all of Hartshorne. Um,
Okay.
so, well, so I think no. So the short answer is no, but at some point in your life, you should do those exercises, or at least like try to absorb what they mean. So I think in his first and second chapter of Silverman, he also like gives you a little bit of like algebraic geometry background that you need to know this, right? So you can try to like internalize the statement without actually going through all of Hartshorn, right?
Okay.
So that's like the alternative to not like reading Hartshorn. But at some point in your life, you should like go through your exercises then, right? So it's okay to take your time on it.
Okay. All right. Thank you. I was just curious because I was gonna read it with a friend, but he didn't want to like take 300 pages of Hartshorn as a black box, and I told him it was probably fine. But I was just curious. But
You'll
thank you.
probably be fine.
All right. Cool.
Whenever,
All right.
whenever you need to, you can go back to it.
All right.
Yeah. Anyways, okay. So yeah. Okay. So this sigma, this is called the Frobenius map. This generates the Galois group of FQ over F. Right? So let's define an elliptic curve. Right? So I'm going to define an elliptic curve by the following homogeneous polynomial. So I'm going to define it as y squared z plus a1 xyz plus a3 yz squared equals x cubed plus a2 x squared z plus a4 xz squared plus a6 z cubed, right? So I'm going to define an elliptic curve as the set of solutions to this equation, right? So note a few things. So this is a cubic equation, right? So this is cubic, and it's homogeneous. Means in particular that it defines a curve, curve in P2, right? So it's in projective space, right? So projective space is basically, you can think of it as the set of tuples, x, y, z, right? Mod some equivalence relation where you're allowed to scale these as you like. So for instance, 1, 1, 1 is the same as 2, 2, 2 in projective space, right? So you can think of it as the set of these tuples. And so an elliptic curve is going to be the set of solutions to this. And just as a notation, if K is some extension of FQ, right, so extension of fields, then you can talk about EK, and this is going to denote the set of solutions to this equation in K, right? Okay, so this is just notation. Right. So what we're going to do for notational convenience is we're going to we're going to dehomogenize this equation, right? Right. And what that means is the following. Whenever you have a homogeneous equation, so let's do a simple example, y squared z plus z cubed, right? So I can divide the whole thing by z cubed, right? And then set little x equal to capital X over z, and little y equal to capital Y over z, and apply this transformation here. So I just get x cubed plus y squared plus 1 equals 0, right? So this actually amounts to, if you notice what this does, is that this amounts to setting z equal to 1 in your equation, right? And so instead of studying solutions to this, right, we're going to study solutions to this one, right, to the dehomogenized version. Now, in the process of doing that, what are we missing? Well, we're missing z equal to 0, right? So let me write down the dehomogenized version of the elliptic curve that I wrote down earlier. So you get y squared plus a1xy plus a3y equals x cubed plus a2x squared plus a4x plus a6, right? And so what are you missing? You're missing z equal to 0. And what you notice is that if in this equation, in the original equation, if you set z equal to 0, intersected with original equation, is basically this point 0, 1, 0, right? And we're going to call this the point at infinity. Okay, so you just think of an elliptic curve as a cubic defined by this equation, along with this point at infinity, which this equation doesn't see. Okay, I'm going to make a couple more reductions, and I'm going to leave these reductions as exercises, right? So if you look at this equation, it's a little bit clunky to write it down every time. But what happens is if the characteristic of your field is not equal to 2, it's not equal to 2, then what you can do is you can write this as y squared equals fx, where fx is some cubic polynomial, right? So you will have to make some sort of transformations over here, right? So like y goes to y plus a1x or a1x over 2, whatever, the right transformation, right? I'd love to work that out. If b is not equal to 2 or 3, and there's an even simpler form, which is given by this ax plus b, or ab are in fq, right? Or whatever field you're the elliptic curve is defined over. And right, so this is called the short y stress form. And a third exercise, if b equals 2, you can check that the best you can do with your transformations is the following. You can write this as y squared minus y, right, equals fx, where f is now a rational function. Rational function. Okay. So, so you can show that in the corresponding characteristics, an elliptic curve can always be written in one of these forms. Okay, so just for notational convenience, I'm just gonna assume that we're in this case, right? Although a lot of definitions make sense even when the characteristics are 2 and 3, but I want to be able to use this equation, so I'm just going to assume from now. Assume that E is given by y squared equals x cubed plus ax plus b. All right, so I defined the elliptic curve, but I lied about something that wasn't a complete definition. So I'm going to insist that my curve be smooth, that E is smooth, right? So which means is that, so this basically means it has no corners. There's an exercise at the end of the notes that actually tells you what the exact equations are in order to determine whether something is smooth. And using that, you can show, that what that means for an elliptic curve, that E is smooth if and only if 4a cubed 27b squared is non-zero, right? So right? So the exercises walk you through this, so don't worry about it too much. So we're going to assume that this is true, and I'm going to define the J invariant, although we won't use it as much. And you have seen this in the password to this set of meetings. The J invariant is defined as 1728 times 4a cubed over 4a cubed plus b 27b squared. Right. And the J invariant is actually a very important invariant of the elliptic curve in that it determines it up to isomorphism over the algebraic closure. Right. So when people study elliptic curves, it's like when people study families of elliptic curves, this sort of becomes extremely important, right? But for now, we're not gonna. This won't come up for us as much. Great. Any questions? Okay, not seeing anything or hearing anything, so I'm gonna go on.
Oh, Soumya, there was a typo at the very beginning. I think it might be also in the notes in the current form in the draft, where the generator of Frobenius was the qth power instead of the pth power.
Oh, sorry. Yes.
Yeah,
You're right.
that's all.
Yeah. Okay, I'm not gonna scroll up enough, but yeah, you're right.
Yeah. Don't worry. And also, is it possible to zoom out a little bit? The writing is a little big. Maybe can you zoom out any in your notes?
It's better.
Yeah, that would be nice. So we can see a little bit more of above. Thank you.
I'm gonna try to write smaller. I don't know if I can. Let's see. See if this helps. Okay.
Right. Thank you.
Okay. Thanks. My bad. Okay, great. So one thing that I'm going to talk about, so is because E is defined by a bunch of equations, you can so E is algebraic, right? So you can talk about functions on E, right? So this is exactly what you think it is, right? So E is some curve, and so maybe you want to think of like taking points and then mapping them to something, right? So they're functions on E, right? So there's like a more complicated way of defining this, but the way we will think about it, right? So we're going to denote, so this is the ring of functions on E is going to be K adjoin XY, so where K is whatever field E is defined over, so modded out by this ideal x cubed minus ax minus b, right? So we're just going to denote this. We're going to think of the ring of functions on E as this ring, and we're going to call it K square brackets E, right? So you can replace K here by FQ, FB, wherever E is defined. And so, yeah. And then you can also talk about the function field of E. And that is basically, I'm going to denote it by K adjoin round brackets E, and this is going to be the fraction field of KE. Right? So whenever you have a map of two elliptic curves, right? So if you have a map between two elliptic curves, and right? So what you can do is you can and you have some function on E, right? What you can look at KE prime. There's an induced map from KE prime to K of E, which basically sends well, if you have some other function G here, right? Oops, my bad. Sorry. Yeah. K adjoin E. Okay. So So you take G, and what can you do with it? Well, you have a function on E, and you want to create a function on so you have a function on E prime, and you want to create a function on E. Well, what can you do? You just precompose with that function, right? So you just take so you take yeah. So you precompose with F, and that gives you a function on E. And if this map is non-constant, right? So if this map is non-constant, then this is actually an injection, right? And so it defines an extension of function fields. So what this means is that if you want to study this map of curves, E to E prime, then you can, so a lot of times what we will do instead is study this extension of fields, right? And then we can apply all of the Galois theory and all of the stuff that we know from Galois theory to this extension of fields, right? So that's sort of the goal of this part, right? Of like studying the function fields of E instead. Okay. Any questions?
Recep has a question. Is there a reason why the coefficients of the polynomial that defines an elliptic curve are indexed not in that order? Why A1, A3, A2, A4, A6?
Classical question. So okay, I think like different people have different answers to this. But my favorite answer is that they sort of are related to these things called modular forms, and so these A1 through through A6 are related to something called modular forms, and the indices correspond to like the weights of the modular forms. So weights. I don't know if Alvaro has a better answer. Alvaro is the go-to elliptic curve person.
Well, my answer typically is that if you look at the entire polynomial and you put weights on x and y, but they come with different weights. So the weight of what is it? The weight of x is 3. The weight of x is 2. The weight of y is 3. Then each monomial has a weight, and the coefficient below a is the weight of that monomial. That has to do with the fact that also when you do a change of variables on the Weierstrass equation, that weight of the monomial comes into play. That when you do a change of variables, just change x and y, you scale them, then sort of like each coefficient changes by a power of that scalar. That is, A1 changes by A1 times that scalar to the first power, A3 changes A3 times the third power of the scalar. So it's helpful. It's sort of confusing the first time you see it, but it's helpful to remember for those changes of variables.
Okay, yeah, that's a much better answer than the one that I gave. Okay, thank you, Alvaro. Okay, great. So all right, great question. So now I'm going to move on to something that's like more characteristic P, and that's something called the Frobenius twist. So if I have E, which is given by, it's given by y squared equals x cubed plus ax plus b, then I'm going to define the Frobenius twist as the following. Y squared equals x cubed plus a to the p x plus b to the p. Right? So So this is called the Frobenius twist. And in general, there's a map from E to EP that sends xy to x to the p, y to the p, and you can check that this is that if xy satisfies this equation, and x to the p, y to the p satisfies this one, right? And so, and also note that, okay, so two things, right? First of all, you can make sense of this any power, or with like any power of Frobenius, right? So you can just do EUP to the R, right? Where instead of raising things to the pth power, you raise things to p to the rth power, right? So you can define it similarly. And second is that if E is defined over the base field, right? So if E is defined over FP, right, then E is literally equal to EP. I'm just gonna write E equals EP. Okay, great. Right, because if you're over FP, then A to the P is A. Great. And so what does that tell us? It tells us that this, so I'm going to give this a name. I'm going to call this prob P. And what this tells us is that prob P acts on an elliptic curve over FP, right? So I can think of it as an endomorphism of E. And and if you make sense of part one, prob Q acts on an elliptic curve over FQ. And so this is going to be an extremely important map for us, right? Okay. So what else do we want to study about elliptic curves? Another thing that we want to study is the number of points. Right? So right now it seems like I'm going through one topic after the other, but the reason for doing that is basically that these are the things that we're going to generalize to higher genus curves later, right? So that's why it seems like a lot of topics all at once. So number of points on an elliptic curve E. So what do I want to do? I want to study the number of FQ points on an elliptic curve that's defined over FQ. And before I go ahead, I'm going to define something called the Legendre symbol. It's the following. So if B is some integer, you can actually define this. Oh, not P. I want a Q here. Right. So this is going to be, so you may have seen this before. So this is going to be 1 if B is a square, or maybe I want to start with 0. So I want to, it's 0 if B is 0 mod Q. Right? This is defined as -1 if B is not a square, mod Q, and 1 if B is a non-zero square, right? Not 0, mod Q. Right? So this is how I'm going to define this. And what you can, and you may wonder why I'm trying to do this. Well, if I fix x inside FQ, right, I want to know when you can get a y inside FQ where such that y squared equals x cubed plus ax plus b, right? That's what it means to be a point on this elliptic curve. So the number of FQ points is going to be determined by whether or not this is a square mod Q, right? Okay, so I shouldn't say mod Q, I should say in FQ. That's probably the right thing to say. You know what I mean, hopefully. So in FQ is the right way to say these. not working in CMOD QC. Okay, awesome. So great. So I want to know when this is a square. So let's define AX as x cubed plus AX plus B, the Legendre symbol corresponding to that. Right? So what we've determined is that the number of points on the elliptic curve, right, is going to be the sum of 1 plus AX over X inside FQ, right, plus something else. But this part, right, the reason for the 1 plus AX is that if AX is 1, which means it's a non-zero square, it means you get two distinct y values because y squared equals x cubed plus AX plus B. Similarly, if AX is -1, then you get no points, right? So that contributes to 0. And if AX is 0, then you get exactly 1 point, right? So that's why it's 1 plus AX. And then we said that elliptic curves also have a point at infinity, which is a rational point at 0, 1, 0. Well, it's an FQ rational point. So plus 1. Okay. So this tells us that this is Q plus 1 plus the sum over AX, X inside FQ. Right? So it becomes the sum of these like easily computable symbols, right? And so you can use this often to compute a lot of different kinds of things about like number of points. Should put size here. Okay. So what I'm going to do is I'm going to let this be equal to something. So AQ of E, I'm going to define this, the negative of the sum of these AXs. Right. And so what this tells us is the size of E of Q is Q plus 1 minus AQ. Right? Sometimes I'm going to omit the E if E is clear. And it turns out that these things are actually very important. And there's a lot of things that have been proved about these. And so there is this theorem, which is called the Hasse-Witt bound. Right? Although for elliptic curves, this was proved by Hasse. And that says that AQ, the absolute value of AQ, is bounded above by 2 square root Q. So what this says is that E roughly has Q points, right? Well, Q plus 1 points, up to an error term of square root Q. Right? So that's one way of thinking about what this says. Right? And so there's the notes sort of like say a little more about what some of the places where these AQs arise. And so if you're interested, a place to look up something. I have 15 minutes, right?
Yep. Yeah, your talk goes until 3:30. It's 2:40 to 3:30. So you still have like 15 minutes.
Okay, great. Any questions so far? Okay. All right, so now I'm going to talk about something called the L torsion of an elliptic curve. And for that, we're going to use the following fact, which is that E comes equipped with any elliptic curve has a group structure.
There is one question, Soumya. Is there any particular reason AQ has that sign convention?
Oh, yeah, that's a good question. So we'll actually see this in like in the next section. So by the end of this place where I talk about the L torsion, this is going to be related to the Frobenius, and then so there is a reason, and we will see it by the end of this lecture. That's the answer. Sorry, I tend to ramble a little bit. Okay. If I don't answer it by the end of this lecture, let me know, and I will talk about it. Awesome. Okay. So E comes equipped with a group structure, and maybe you've seen this on like the covers of various books, at least when E is defined over R, or you can think of like the R points of E, right? I'm going to draw the real picture because I feel like I'm obligated to draw it whenever I'm talking about elliptic curves. But if you have a point P and you have a point Q, then the way to determine the group structure, or how you determine P plus Q, is the following. You just draw a line through these, and then there are some theorems that tell you that it will necessarily intersect the elliptic curve at another point. Now, this point can lie on the elliptic curve, or it can be the point at infinity, but there's definitely some point. We call this R, and the group structure is determined by setting P plus Q plus R equal to 0, right? Where 0 is the identity, and this is taken to be the point at infinity. Right? And you can show that this satisfies the usual group properties. And so maybe you're wondering, well, I've been defining an elliptic curve over a finite field. This picture does not make sense over a finite field. What do you do then? Well, you can still make sense of this algebraically, right? So if you write down the coordinates for P and Q, you can write down the equation of the line that passes through them, and then you can see where that line intersects the elliptic curve. So all of this makes sense algebraically, and so you can use the same equations that you get from this picture in order to actually determine the group structure, even for other fields. Okay. So we're just going to use this fact. What this allows us to do is that it allows us to talk about things that you can talk about with groups, right? So for instance, there's a following definition. So if you have two elliptic curves, a map between them is called is an isogeny, right? If it satisfies the following conditions, it is a homomorphism, right? B, it's surjective on FQ bar points, right? And has finite kernel. For phi, right? So if you look at these physically, you look at the physical points that are inside this kernel, right? This is finite. Right? So that's what an isogeny is. So we've already seen an example of an isogeny. And an example is the Frobenius map from E to EP, right? This is an isogeny. An exercise sort of walks you through what this isogeny is, and well, also the degree of the isogeny, which I'll define in a bit. The other example is multiplication by n, right? So you can take a point P and map it to n times that point. And this also turns out to be an isogeny, right? And so given an isogeny, you can define the degree of the isogeny. So remember that we talked about whenever you have a map of two elliptic curves that's not constant, right? That doesn't extend everything to 0, for instance. You get a map of function fields, right? You get a field extension. So the degree of phi is defined to be the degree of this field extension. And so if you go back to our examples, then it turns out, so it turns out that this is an isogeny of degree p. This is an isogeny of degree n squared. Right. So the exercise also walks you through this part. This is a little more complicated, so I won't really talk about that. Yeah, so it's an isogeny of degree n squared. Okay. Well, do you want to sit and compute the degree of the field extension every time? Maybe not, right? Here is another way to think about this. So if degree of phi and p, which is the characteristic, are coprime, then it turns out, so this is a fact, that then the size of the kernel of so you look at all the FQ bar points, right? Inside the kernel, and the size is exactly equal to the degree of phi. Right? So if you literally count the number of points that map to 0, you can tell what the degree of phi is. But you need this coprimeness condition. Right? So putting all of this together, what this says in particular, if n and p are coprime, then if you look at the kernel of the multiplication by n map, right? So this is often called the n torsion. So this is called the n torsion of the elliptic curve. Then the kernel is actually isomorphic to z mod nz squared. Right? So we have to take FQ bar points here just to be careful, but basically all of the things that map to 0, there's n squared of them, and it's isomorphic to z mod nz squared. So what are we going to do with all of this? We're going to take this information and we're going to package it into one single object, right? So the definition of something called the Tate module, right? So let's say L is some prime that's not equal to P, right? So we know that from this above observation that EL to the n is isomorphic to Z mod L to the n Z squared. Right? Further, notice that we have these maps. So if you have EL to the n plus 1, right? So this means, oh wait, I didn't define what E, sorry, my bad. So by E, so this I'm going to write as En. So this is standard notation, right? So this is the n torsion, the elliptic curve. My bad, sorry. Great. So if you look at the L to the n torsion, then this is isomorphic to Z mod L to the n squared. And then from the L to the n plus 1 torsion, you can construct a map to the L to the n torsion by sending by basically multiplying whatever you have by L, right? So this is the map. And so if you have a bunch of these maps, what can you do with them? Well, you can put them into an inverse system, right? Yeah, one put the plus one. I can take the inverse limit over all of these, right? And this is called the Tate module. And so by this observation, this is isomorphic to ZL squared. Okay, so why do we do this? Well, one of the reasons to do this is that, well, look at what we've done, right? We've taken an elliptic curve, which is like an algebraic variety, etc., and we've converted some of the information into something that's essentially linear, right? So for instance, if you want to study maps on E, so an example is the Frobenius map, right? So recall that we talked about the Frobenius action on E. Instead of studying it here, we can study it on TLE. Right? I'm going to call this Frob QL. And so, right, so because if E comes with an action of Frobenius, then it turns out that each of these L to the n torsion subgroups, these come with an action of Frobenius as well, right? And then all of those actions sort of you can put all of them together and get an action on the Tate module itself. And so instead of studying things here, instead of studying things on E, you study things on TLE. And what that gives you, is that you can now think of this as a matrix with coefficients in CL, right? So you can think of, so you've somehow linearized your problem a little bit, right? So you can get a lot of information, and we like it. We like linear algebra. We can do linear algebra. Other things are hard, but linear algebra is relatively doable. Okay, so here is the proposition, right? You consider this matrix, so Frob QL, right? So since it's a matrix, you can consider its characteristic polynomial, given by the following. I'm going to call this PEQT. This is T squared minus AQT plus Q, where these AQs are the same. So they appeared in the expression for EFQ. And so, okay, I don't know if this is, I don't know how you feel about this, but this is like a really cool thing, right? So somehow you looked at the Tate module, you constructed it somehow, and then you looked at this matrix and looked at the characteristic polynomial of this matrix, and it turns out that the trace of this matrix is somehow related to the number of points on E, right? And I think that's super cool. Right, so this is like one of the really cool things, right? And so this also sort of explains the sign convention question asked earlier, right? So you want to realize this as a trace, which is why you want it to be like minus AQT. So notice that, so let's talk about a few things. So first of all, the size of EQ, EFQ, right? This is Q plus 1 minus AQ, which is PEQ 1, which is kind of reasonable, right? What is an FQ point? Well, an FQ point is something that's fixed by Frobenius, right? By Qth power Frobenius, you need x to the q, y to the q is equal to xy. So somehow it's like the fixed part of, so it's the points that are fixed by Frobenius. And so Frobenius acts trivially, so you plug in a 1 and you should get the right number. Second, notice that this, I didn't say anything about L. Right? And so this sort of, right, so the from QL, right, no matter what L is, always has this, as long as it's different from P, always has this characteristic polynomial. So it tells you that the Frobenius acts in the same way on all Tate modules, right? So as long as L is different from the characteristic, you get the same polynomial. So this is like, yeah, so it's part of a greater philosophy. Because of lack of time, I'm not gonna say anything more about that. But the last thing that you should notice is that this is a polynomial defined over the integers. And in particular, this tells you that the eigenvalues of the matrix values are algebraic integers. Okay, so those are the 3 things that I wanted to observe about this. And tomorrow, we're going to talk about curves of our genus and eventually talk about generalizations of all of these sections that we talked about for in this lecture. So I think I'll end there.